At the heart of the MIT campus, deep in the basement of Building 5, a red, fiery eye is watching us all. Luckily for us, it is not the Eye of Sauron, but a miniature iris that has been developed in the Raman lab. This iris is composed of muscle fibers, which are organized in different zones. On the outskirts here, you have radially oriented fibers. A bit more inwards, there are concentric fibers, and then in the center, there is a hole that symbolizes the pupil in our eyes. So how can muscle that we grow in vitro in a lab take such an intricate orientation? Well, that's because we provide it with directional cues throughout its development. More specifically, we have developed a simple patterning method that relies on 3D printed stamps with microscopic grooves at their surface. To maintain the cells in optimal conditions in their development, we actually grow them on a gel that is a bit similar to gelatin, which resembles the extracellular matrix they feel in our body. So we apply the stamp on the surface of this gel, we let the gel solidify, then we peel off the stamp, and we can see that the pattern has been nicely transferred to the surface of the gel. And now Laura is going to tell us more about how the cells actually grow and align in these patterns.
Thanks so much, Tamara. On these newly patterned substrates, we first place young myoblast cells, which are the progenitors of mature muscle fibers. The myoblast cells then feel the signals from these grooves and then fuse and align into mature fibers that orient themselves along the directions of the groove we've actually placed in the substrate. And using these aligned fibers, we can get a variety of different versatile functions. As you can see in these pictures here, the unstamped substrates below the muscle, we have the skeletal fibers orient in every which direction randomly and twitch in every which direction as well. However, if you actually align the muscle using our technique, you can see that you can get controlled direction in the direction that you engineer the muscle. And this leads into how we then made the iris muscle, where we can actually pattern a variety of different directions, as Tamara explained before. And there's a lot of applications for this technique outside making, eyes that can take over Middle Earth. Specifically, we see having the ability to create motion in a variety of directions useful for robotics, right? Where we can use biological tissues to create movements in controlled directions. Also, it is useful for tissue engineering, right? Where we can now make in vitro muscle that is more similar to the muscles in our body that have controlled directions and let us move in a variety of different ways. And of course, now that we can have more consistently aligned muscle, we believe this could be useful for drug screening to create more consistent drug and repeatable drug screens. And that brings us to the end of this presentation. And of course, it ends with our acknowledgements because, well, Tamara and I are the ones presenting here today. This work couldn't have happened without all the members of our lab and our funding sources. Thanks so much for listening.